Hello all learners, welcome to our session of methodology and GD&T approach. In today's session we'll deal with limit fits and tolerance. So basically we'll start with the basic terms related to our limit fits and tolerance. So in spite of advancement in machine tool technology, we have impossibility to achieve the dimensional perfections. That means for any type of a product which we manufacture, we are unable to get the exact dimensions. So for that purpose we have to go for limit fits and tolerances, though we have to adapt some of the extra cost of the product, but the dimensions which are to be maintained within a very close degree of accuracy, we require a lot of time. So again, the function aspects of component can be achieved even without going for its exact dimensions. And when the assembly of two mating parts is to be done, so a kind of permitted variation has a very much important significance. So that's why we have to go for provision of tolerance on different components. Again, we know that no component is identical in nature, so tolerance and its calculation plays a very vital and important role in production. So for understanding limit fit tolerance, we have to understand few of the basic definitions related to that. So first one is the size. So what exactly size means? It's nothing but a number which expresses the numerical value of any sort of a dimension. In that, a nominal size is used for the purpose of identification of a component. That means specifically that component size is represented or highlighted on a component. The nominal size of a dimension or part in the size by which it is specified in a drawing. Then we have a basic size. It's usually the size with some sort of a reference. So in over here we have a 0 line as a reference. So from that position, if you mention any dimensional and numerical value, it will be called as a basic size. In that, this diagram is very much important. If we have a hole as an external feature, internal feature, and a shaft as an external feature, so every component, what I said earlier, has some of the tolerance provided on that. So if we consider a shaft over here, so highlighted hatched portion has some sort of tolerance we call. So the below portion is nothing but the minimum limit. The above line, exactly maximum dimension we call, is an maximum limit, and difference of both we say as a tolerance for that. This one again, a few of the important part which we have to discuss in our further discussion is lower deviation and upper deviation. We have a standard basic line called as a 0 line over here. So reference from this to the size of any of the component, we call it as a basic size. That is, this is the basic size of a shaft. Then the distance from a maximum limit of any of the components, suppose this is a shaft, we have a maximum limit line over here. So distance from this line to 0 line, we call it as an upper deviation. Similar case over here. So maximum limit for hole is this one and 0 line is over here. So this distance we call it as an upper deviation. In vice versa, we have lower deviation. So lower limit distance to 0 line. This gap we call it as an lower deviation. And one important term, the difference between the two sizes components, we call it as an allowance. It may be positive or negative. So coming to the basic terminologies, actual size is nothing but we can call it as a measured size of a component, whose component size is measured with help of any of the instruments which we have discussed in our earlier videos. Then actual deviation, the exact deviation from the basic size. We have upper deviation as I discussed earlier, that is difference between the maximum limit and the corresponding basic size. Then we have a lower deviation and a 0 line, which is nothing but a standard basic line, which is a graphical representation for limit fits. Then tolerance, that is difference between maximum and minimum limit of the size. So limits are classified as maximum or upper limit, and second case as minimum or lower limit. So maximum limit is nothing but the greater value for the two limits, that is maximum permissible size for a job and minimum permissible size for a job as minimum limit. This is a very much simple term which can be remembered. So this is an hole as an internal feature. So this is the maximum limit, this is the minimum limit, and difference of both we call as a tolerance on hole. Then we have the tolerance on shaft, that is minimum limit and maximum limit. So difference between these two we call it as a tolerance on a shaft. Now except regarding tolerance, so it is very difficult for an operator to manufacture a component at an actual size. So the production machines themselves have some sort of inherent accuracies in them and have limitations to produce a perfect part. Likewise, so variation in the component properties of the material being machined introduce the errors. So to compensate for those errors, we provide the tolerances, and the basic tolerances are classified as unilateral and a bilateral tolerance. Now unilateral tolerance, if we consider for a shaft, will be represented in this fashion, that is either one of the limit will be 0, or either both will be positive, or either both will be negative, we say. So this is the 0 line, this is the representation style. Above this we have a tolerance on shaft, or either below this we have a tolerance on a shaft. So that means unilateral tolerance represents the tolerance provided on either side of a 0 line. Then we have a bilateral tolerance, so tolerance which is provided by bisecting the 0 line, or either we can say that the tolerance provided one will be positive, other one will be negative. Then we have classification of fits. So fits is basically nothing but a degree of tightness or looseness between the two meeting parts. So when we have a fitment of any two components, say cylinder and a piston, or either uh, we have a wardrobe, or either we can say any two components combines together, so whether it freely slides inside each other, or either we have to apply some sort of external force. Based on that, we have the different classification of fits. So clearance fit, transition fit, and interference fit, these are the three basic types of fits. So in that clearance fit, we always remember the maximum limit of external feature, that is shaft, is smaller than the minimum limit of an internal feature called hole. So difference between the two sizes we call it as a clearance, and it should be positive. So this is a clearance fit. Similarly, we can have some sort of dimensions over here. Then we have the different representation style, as suppose if you observe this, so hole minus shaft sizes should be greater than 0, then we'll have a clearance fit. So there are number of examples for this. We have a loose type of a joint in a clearance fit. So loose fit, running fit, sliding fit, and medium fit are basically classification of three clearance fits. So agricultural equipments and loose pulleys come under the category of clearance fit. Running fit we have bearing pair. Then slide fit or medium fit, which come under the category or some of the applications as slides, slide walls, and automobile parts. Similarly, the differentiation with the help of numerical evaluation is shown in this slide. Then interference fit. So how to understand interference fit? So minimum limit of the external feature as a shaft is greater compared to the maximum limit of a hole at its internal feature. That means so combination or fitment between this will be with the help of some sort of external hammering force, or either the different external forces are required to get the fitment. So this comes under the category of interference fit. So in such cases, the diameter of shaft is always larger than the hole diameter. So hole minus shaft is less than 0. So interference exists between the high limit of a hole and low limit of a hole. So some of the examples or classifications we can say shrink fit or a heavy force fit, which is fitting of reams. Then we have a medium force fit, which is under the car wheels or dynamos or armature. Then tight fit, that is keys, pulleys, shaft, and rocker arms. Then we have transition fit. It is most of the intermediate fit between clearance and interference, in which we have the interference of maximum limit of a shaft and minimum limit of a hole. but the maximum limit of a hole does not interfere between the minimum limit of a shaft. So we'll try to understand, that is, transition fits are comprises between the clearance and interference fit. So push fit we have, snug fit we have between the moving parts which shows least vibration, we have a force fit, then we have a ringing fit. So ringing fit most probably we may get it as fixing the key by a press fit, or simple very much our used application is our pen and cap. Then we have provision of tolerance based on two systems, that is hole basis system and second one as shaft basis system. So in hole basis system we say that the size of a standard hole is kept constant, and then we classify the size of the shaft. So if we want a type of fit, we can simply vary the size of a shaft to obtain a basic fit. Suppose if you want a clearance fit, we can reduce the size of a shaft. If you want an interference fit, we can increase the size of the shaft instead of touching or instead of changing the dimensions of a hole. This is the basics of hole basis. Then we have a shaft basis system in which shaft remains the constant, that is basic size shaft remains constant, and then we can obtain the types of fits in this similar fashion. So basic differentiation, we can have capital, that is less amount of capital and storage space for tools are required to produce holes, and whereas in shafts capitals and storage space for large number of tools which are required for this. Then we have very much easy to vary the shaft size, but it is very difficult to vary the size of holes. So most probably we go for hole basis. So size of the hole views over deviation or fundamental 0 is assumed as a basic shaft. That means in terms of H hole, we'll try to understand what does exactly H hole and H shaft means in our next slides. So gauging of shafts can be easily and conveniently done with the help of adjustable gaugings. So these are the following differentiation and why we go for hole basis instead of shaft basis system. So for successful implementation of limits and fits, the following conditions must be always satisfied. Please remember. So for different types of fits, each basic size of hole and shaft must have a range of tolerance values. Then second thing is the system should cover the available ranges of the sizes for various applications, and the tolerances selected for both unilateral and bilateral should be acceptable by both the hole basis and the shaft basis system. Then we have system should be suitable for rough and high precision work. So if these following conditions are satisfied, then we can go for it. Then interchangeability, as we discussed earlier, no component is identical. So interchangeability is to be followed between the any two components, that is mating components. So when a very few assemblies are to be made, the correct fitment between the two parts can be controlled with the help of the sizes while machining. Then we have a method of manufacturing which takes more time and will therefore increase the cost. So this may be a drawback, we can say. Then what are the advantages for this? We have assembly of mating parts is easier, enhancement in the production rate, standardization of the machine parts. Again we have bring down the assembling cost, then repairing of the existing machines and replacement of the worn out parts. So other limit systems which are followed in different countries, we have American National Standard Association follow the tolerance system, then we have a British standard, then we have ISO standard and the New World system. So out of this, most probably we follow New World ISO systems. So for that we have to understand one simple diagram that is related to fundamental tolerances. From this we can remember holes are represented with the help of capital alphabets or letters, then shafts are represented with the help of a small letters or alphabets. Most probably we have fundamental deviations categorized into 25 types. We'll try to understand these are the classifications. So this is nothing but the fundamental deviation diagram for a hole and this for a shaft. So what does this represents? The y-axis is nothing but the fundamental deviation, and the x-axis represents the zero line. So in this case, the portion above the zero line is always positive and below the zero line is always negative. Now try to understand one thing. So small alphabets represent shafts which start from the left bottom corner, whereas whole representation of tolerance starts from the left top corner, and which will end at ZC. So what I was talking earlier, that is H is the basic size, basic hole and basic shaft over here. So gap between, and what does blocks will represent, try to understand. This block represent the tolerance. If we try to understand B type of a shaft over here, so this top portion indicates the upper limit for that shaft, and this basic bottom indicates the lower limit of the shaft. So ES represents the deviation, which is upper deviation over here. So distance from the upper limit, as we discussed, to the zero line is nothing but the upper deviation, which is represented as ES over here. And since shaft is represented by small alphabets, it's a small es, whereas in holes we have capital Es, which represents the upper deviation for the holes, whereas Ei with respect to shaft as well as with respect to hole represent the lower deviation of a shaft and a hole. So lower limit to the zero line, that is lower limit to a zero line, represents the. Now out of this Es and Ei, which one is very much closer to the zero line is nothing but a fundamental deviation. So final target from this figure to understand is the minimum distance of a low limit to the zero line is a fundamental deviation. So H whole wide is called as fundamental because its deviation, that is lower deviation over here, upper deviation is 0. So H is nothing but we say as this one, fundamental deviation as 0. So this line indicates the lower deviation, this line indicates the upper deviation. Over here we have this distance as upper deviation, this to this we have a lower deviation. So A to H we have Es as a fundamental, and from K to Z we have a upper. So following things can be understood. So this diagram was very much important to understand because a few of the numericals will be based on this diagram only. So finally what we have to understand is the fundamental deviations, and the values for each fundamental deviations can be understood again. So this was all about the fundamental deviation part. Now what is to be understood is how the tolerance can be provided. So each of the 25 holes has some sort of 18 tolerances, which are designated as IT01 to IT16. So total 18 tolerances, or we can say grades of tolerance. So tolerance grade means what should be the height of each block. Suppose if we will consider the height of this B tolerance, so how much should be the distance? So that is decided based on the 18 grades. Now that a numerical letter will be provided in front of the alphabet of a hole or a shaft to understand. So we can find out the tolerance, upper limit, lower limit, and difference of that as a tolerance. So that is nothing but standard tolerance. So to find standard tolerance we have some sort of expression as I, which is equal to 0.45 cube root of D plus 0.001 times D. So I will be equal to standard tolerance and can be found out this. In that case we will require D, and this D is nothing but the standard geometric mean of two different diameters. Now what exactly D and how to calculate it, we will discuss this in our next session. But important again to remember is I will be always represented in microns, or what we calculate will be in microns. So you have to convert this value of I into millimeter for the calculation part of our tolerances. So the detail of these tolerances and the diagrams which we discussed earlier will be understood again in our next session. So different clearance, fit, and transition blocks we can obtain. This is the fitment, so you can remember this. With the reference for this is nothing but RKJ and metallurgy book. We can get it over here. So clearance fit can be obtained with this, or transition over here, and interference fit. So thank you.